Okay, today we are going to be solving for our missing variables using the information from this image. So we know that this object is traveling 70 meters per second initially at a 50-degree angle. So let's go ahead and fill out everything that we can up to this point. We don't know our initial or final velocity in the y direction because this 70 meters per second is a combination of our y and x velocities. It's at a 50-degree angle. So we can't actually put this in for our y or x velocity. But we do know that our acceleration in the y direction is negative 9.8 meters per second squared. And our delta y, since it leaves the ground and comes back to the ground, is 0. And we don't know time, so let's move over to the x direction. Now, the velocity in the x direction, at least with projectile motion, is always constant. If the velocity is constant, our acceleration is going to be 0. Because acceleration is the rate at which velocity changes. If our velocity isn't changing, we're not going to have an acceleration. Okay, so now this is really all that we can get so far. So we have to use trigonometry to get the rest of this. This 70 meters per second is the magnitude of our resulting velocity. So we need to draw our triangle, and 70 meters per second is going to be our hypotenuse. And the line that goes across the bottom is our x, right? It's our horizontal component. And our y is going to be the vertical component. So we are trying to solve for y and x here. And we know that this angle is 50 degrees. Alright, so what we need to do is solve for y and x using trigonometry. Well, we need to write our trigonomic functions. We have sine theta equals opposite over hypotenuse, and cosine theta equals adjacent over hypotenuse, and tangent theta equals opposite over adjacent. Now you can reformat these first two to say basically the opposite, our opposite side is y and our adjacent side is x. So we could say that the hypotenuse, if we took this hypotenuse and put it on the left-hand side, our hypotenuse sine theta equals y, and hypotenuse cosine theta equals our x. So now we can plug this into our calculator. Let me move this over so we can solve. Alright, so what we're going to do is hypotenuse. Our hypotenuse is 70. Sine 50 is our y velocity. Oh, wait, hold on a second. We need to check our mode. We are in degree or radian mode. We need to be in degree mode. Alright, so let's try that again. Alright, 70 sine 50. There we go. And we get 53.6. So we know that our y equals 53.6 meters per second. Alright, then we'll do 70 cosine 50 to get our velocity in the x direction, we get 44.9. We'll just call that 45. 45 meters per second. Alright, so now we can fill out our x and y columns a little bit better. So we know that our initial velocity in the y direction is 53.6. I'm going to go ahead and undo that. That wasn't a very good 5. 53.6. And if it leaves the ground going 53.6 and goes all the way back up, and your velocity in the y direction here is 0 meters per second, but then it starts falling all the way back down. So it's going to be the opposite of the beginning, negative 53.6 meters per second. Alright, and we know that our x velocity is 45 meters per second. And since velocity in the x direction is constant, our final velocity is going to be 45 meters per second. Alright, so now we need to solve for time. Our delta y is 0, and so we're going to want to choose an equation without delta y. This equation happens to be, let's see, final velocity equals initial velocity plus acceleration times time. So our final velocity is negative 53.6. Our initial velocity is 53.6. And then we add that to negative 9.8 times time. Alright, negative 53.6 minus 53.6 it is not 0. It is in fact minus negative 107.2. And that is equal to, since we got the 53.6 off that side, 9.8 times time. So at this point, to solve for time, we just divide both sides by negative 9.8. And when we do that, we get 10.9 seconds. So we'll go down here and say our time equals 10.9. Now, our time is the same for the y direction as it is for the x direction. So when we solve for time in the y, we can put 10.9 for x. And now we want to know, how far does it go? What's our delta x? When the ball left the ground, how far did it end up landing away from where it started? So what we're going to use is a very simple equation, actually. Whenever we have an initial velocity and a final velocity that are the same, like this, our x velocity is 45, we can actually use a very simple equation. It is velocity equals distance over time. And we know that our velocity is 45 in the x direction, which is the delta we're trying to solve for. and that our time is 10.9. So all we have left to do is get d on a side by itself. So what we have to do is multiply both sides by 10.9. So we're going to end up with 45 times 10.9. 45 times 10.9, and our object lands 490.5 meters away. So delta x is our d, and it is equal to 490.5 meters. Alright, and we're done.